We are studying operational amplifier. We are studying analog integrated circuit, and in first video we have studied the introduction of opamp. What is opamp and what are its different applications? So it is an integrated part of analog electronics. We can develop different applications which are required to run our day-to-day applications by using opamp. In this video we are going to study the block diagram of opamp, and I want to show you what is inside the IC. Behind this small IC, what exactly lies, what kind of circuit is there. After that, we are going to compare some ideal characteristics or ideal parameters of op-amp with practical parameters. So let us begin with the block diagram of operational amplifier. This is the symbolic. This is the symbol of op-amp having two power supplies, and it is V1 and V2 are two DC inputs are shown here. The first stage of this block diagram consists. It is made up of two hardwares, two circuits, or two stages. The first stage is differential amplifier itself. This differential amplifier, it picks up the input, or it picks up the difference between the two inputs, V1 and V2. Here, these are the DCs, okay? And we are studying the DC analysis of op-amp. And in later stages, we'll be applying the AC inputs along with this DC. This VC plus VCC and minus VEE is the DC bias voltage, whereas this V1 and V2 will be the actual AC inputs having some frequency variations. So this is the differential amplifier. So differential amplifier, it consists input stage and intermediate stage. Okay. So what is the task for this differential amplifier stage? It picks up the difference signal and provides very high gain, and it offers with high input impedance. Okay, and this input impedance is very high. What are the advantages of input impedance? We have discussed in the first video, and in the second in the third video also we'll be studying the input impedance, and here itself we are going to write equation for input impedance and input resistance. Open loop gain A is infinite. Okay, so this is designed to obtain the infinity open loop gain. When we are not using feedback, we are not connecting some part of output to the input. So in this fashion, it is designed and it is an open loop condition. And ideally, the gain is infinite. And the second is the level shifter. So what is the level shifter? Actually, this op-amp is a direct coupled amplifier. We are not using any kind of capacitors. I will show you the circuit diagram of input stage, and then you will see that there are no capacitors between input and the actual transistor where we are applying the input. So it is a kind of a direct amplifier. It amplifies a DC also. Okay, therefore this level shifter is required here, and it adjusts the DC bias level of signal from gain stage to ensure the output is centered around the 0 volts. Okay, what is the meaning of this? So this is the electronic circuit, and it has some biasings. Okay, by adjusting the some voltages by using some capacitors and resistor values, the operating point is adjusted in the center, and so that we can get the distortionless output. Okay, and it is the level shifter which perform this condition of maintaining the DC conditions of the circuit. So next block is the output stage. So output stage of amplifier, specifically it boosts the uh, voltage level, okay, so that we can drive the next circuit. The final stage drive the load connected to the op-amp's output, okay, and it provides low output impedance. What is the how the design, how the circuit or how the output stage is designed? So it will keep the output voltage, output resistance or output impedance as low as possible. Ideally it should be zero, but practically it won't be zero. Okay, and it has a high current capability to handle various loads without significant voltage drop. Okay, so this op-amp is designed in such a way that we should get the maximum voltage from this, maximum amplified voltage from this. Okay, so that is the design of this op-amp. And this second stage, okay, the transistors used in the last stage from where we are taking the output, they are used in class B push pull amplifier. Okay, it is a kind of power amplifier, and it is called class AB mode, and push pull pair is used for this power amplification. Okay, so this is the power amplification. And what is the behind this IC? Okay, So this is the symbol of IC we are using here. And whatever we use, the circuit inside the IC, it is like this. So it consists bipolar junction transistors. So here we are applying the input voltage. See this. So V1 we are applying and V2 we are applying here. So these are the transistors. No capacitors are used here to apply the voltages. Okay. Now when we are studying the parameters, we are applying only DC voltage, but it is made to amplify the signals having some frequencies. Okay. Using the before starting studying the applications of it, we are at the stage of studying its DC parameters. Okay. And so that we can use it properly and we can understand it and we can design and develop new applications by using this IC. So these are the BJTs used. The circuit can be designed manufactured using the MOSFETs also. Okay, the circuit using MOSFETs is having different parameters and it has a high performance thing. Okay, as compared to BJT. So this is the BJT, specifically 741 is made using this BJTs. So this is the older version of the circuit, and this states having some okay offset null are here, which offset null pins are available in the IC. And see output, sorry, this plus 7, IC pin number 7 is having plus VCC. So here it is plus VCC, and here pin number 4 is minus VEE. So these are the DC voltages required to turn on the transistors present in the circuit. Okay, and the pin number 6 is taken from this, and it is the output we are getting amplified version of the signal present at V1 and V2. Okay, and depending upon the polarity of this, if V1 is greater than V2, so output we are getting here. So here we are getting the output voltage. So V0 will be in phase with the input, difference input voltage. Okay, and that is called non-inverting input. When V2 is greater than V1, the difference will be negative and we'll get the output voltage out of phase. Okay, and this kind of voltage which is 180-degree out of phase with respect to V2 is called as a inverting input. Okay, this input or whatever we are applying here, it will be inverted. Okay, by 180-degree phase difference. And how the circuit is made inside the IC, how it is manufactured, it's a different thing. Okay, so it is VLSI technology, very large scale integration technology is used to manufacture this. Actually, this circuit, which is shown on the left side, uses the symbols of transistors. These are not transistors, these are the symbols of transistors. Actually, how circuit looks like or how transistor looks like inside the IC. So it is like this. So these are the transistors used here. Okay, the circular structures represent the transistors. And here it's a high gain stage, consists of various transistors and capacitors are here. Okay, this is a kind of capacitor. So you will study these things, how it is manufactured, how it is what are the different stages of manufacturing the IC. Actually you will study in the VLSI subject. Okay, this output stage and this is the output, and short circuit protection is additional circuit so that IC will not be damaged for uh, input variations or wrong connections. Okay, this is the internal view of the IC. Then you understand that we are using symbol and we are having different circuits using symbol. What is inside the IC is a very big circuit. Okay, remember this. And this is the representation of op-amp. Okay, so it is ideal and the practical equivalent circuit of ideal op-amp and practical op-amp. Let us understand what is the difference between this. What are the expectations for which the IC is designed, and what are the expectation uh, or what happens when it is performs the actual performance in the hardware. So here we have DC sources. Okay, this is plus minus V1 and V2, and currents are flowing through this. Let us say it is suppose IB1 and it is IB2. Okay, these two currents. So this terminal is, it is a non-inverting and it is an inverting terminal. So what is the voltage between this? The voltage between this is the difference voltage here. So it is VID. So what is VID? So VID is the differential voltage. So it is V1 minus V2. Okay. And this VID, what is the output voltage? So output voltage will be A times of VID. It means V0 is A times of V1 minus V2. Okay. So this is the equivalent representation using Thevenin's theorem. And here it is open circuited between these 2 points. There is no resistance shown here. That is the ideal case. Okay. It shows that infinite input impedance. So it is called input impedance is denoted by Zi, and it is ideally it should be infinite. Okay. We can call it as a Ri also. So Ri is infinity. Whenever we talk about the DC conditions, Ri is used when we talk the use of IC, when input AC is applied, at that time it is input impedance. Okay. And what is the expected thing ideally? Ideally, output impedance should be zero. Now, infinite open loop gain. So we have discussed this. It is infinite open loop gain when we are not using any kind of external components. This circuit is made to offer the infinite uh, open loop gain. It's ideal condition. And one more parameter is there, and that parameter is called as a common mode rejection. We are going to study this in detail. Okay, CMRR. We are going to discuss in detail, and it's having infinite bandwidth. What is bandwidth? Expected or ideal, it should be infinite. Now let us talk about the practical uh, op-amp. So practical op-amp is having resistance here. See this input resistance, or we can say input impedance. So it is V1 and it is V2. Okay. And here it is the RS. So this RS is a part of source. Okay. It's not part of IC. And here it is VID, input difference voltage, and currents are flowing through this one. Okay. So it is having practically it is having some resistance. And what is the resistance? Practical resistance. So it is RI. Differential resistance, input resistance is given by, it's a VID, okay, or simply we can say VI divided by input current, okay. So it is I in. I in is the input current. So this is the DC condition at omega equal to 0. Approximately, there is no frequency and frequency is 0. This condition, the input resistance word is used. Now let us talk about what should be the input impedance. Ideally, it should be infinite. Input impedance is infinite. So it is Zi is input impedance, and it is given by uh, R in divided by 1 plus j omega R in into C in. What is R in? So R in is the input impedance, input resistance. At DC condition, or only DC voltage is applied at V1 and V2. So it is the input impedance. Now, what is the C in? C in is the input capacitors. So it is capacitance. What kind of capacitance? It is the input capacitance. Okay. And what is omega? So here, so Zi we are talking about the omega is not equal to 0. Okay. So this is the input impedance. Now what is when frequency is not equal to 0, when input frequency is not equal to 0, what happens? Which one is greater? Zi is less than Rin. Okay, this Rin divided by these factors. Okay, the frequency is a denominator. If frequency increases, what happens? The Zi decreases. Okay, so input impedance is less than the input resistance when for this condition. Okay, and this is the input impedance is the frequency sensitive, and it depends upon the uh, particularly it is depends upon the frequency. We can say. Okay. And what about the input resistance? So input resistance, these things, okay, in terms of transistor parameter, we can define this. Okay, will write here. So input resistance, RID, okay, once again, I'm writing equation. So it is differential input resistance is VI divided by, or we can say VID divided by I in, total input current. Okay. In terms of transistors parameter, it is given as VT, it is given as beta VT divided by IC. Okay. What is IC? So IC is collector current of transistor. Okay. So we are going inside the IC and we are talking about the transistor. What is VT? So it is voltage equivalent of temperature. We know that temperature affects the semiconductor device performance. Voltage equivalent of temperature. Okay, it is around 26 millivolt for semiconductors. Fine. And what is IC? So IC is beta times of IB. Okay. So what is IC? Beta. Beta is the current gain. So beta is nothing but, so it is IC divided by IB. Okay. Now, why this we are writing, why we are talking about the IC? Because temperature changes, then it will change the input resistors. Okay. So these are the DC conditions of op-amp. So let us talk about the output resistance. So what is the output resistance? Ideally, it should be 0. Okay. So output resistance are not equal to 0. So this is the ideal condition. And what is practical? So it is R naught depends upon the output voltage divided by output current. So this is the output resistance. Okay. It should be very low. So it will be practically it is having 50 ohm of value. For MOSFET, even it is lesser than 50 ohm. Okay. If output resistance is high, what happens? The voltage drop occurs. Whatever the voltage is amplified by op-amp, it will drop in IC itself. And we can say it will sink. The IC will act as a sink. Okay. Instead of working as a source. Okay. So this is the source for amplified voltage. Therefore, for voltage amplifier particularly, output resistance should be 0 or close to 0, should be small, and input resistance should be high so that it will not load the source. Okay. So this is the about the output resistance. What about the gain? So gain is nothing but, so it is the output voltage divided by input voltage. So what is output voltage? So it is V1 minus V2. Okay. Sorry, it is output voltage. Actually, it is VID and it is V naught divided by V1 minus V2 because it is the difference voltage. Okay. So what is the output voltage? How much will get? A times of V1 minus V2 will get this. Operational amplifier, its basic design is for amplifying the difference present at its two inputs, inverting and non-inverting input terminals.